So let's now move from root finding to nonlinear optimization. We will discuss the unidimensional optimization case here, where we have a univariate variable where we want to see at which value of this the function is maximized. And then we'll move on to discuss the multidimensional cases. So the optimization problem is very related to the root finding problem. Suppose we want to maximize a function fx, and for example, it's in this form with a lot of logs. A graph can show that the maximum of this function is attained somewhere between 2 and 10. So here's just the code for creating the function f, which takes value x and outputs fx. And we'll create a sequence of x values from 2 to 10, and we will evaluate the f function at each of these values. So here's a plot of this curve between this interval. And you can see that the maximum is somewhere around here, but you can't exactly eyeball that. We can always use grid search to find the point where fx is maximized. This is given by the xx value, at which point the fx value attains its maximum. And we can see that in this case, the maximum is attained around 5.79. However, grid search can be slow and it doesn't generalize well to multivariable functions. So for one dimension, say we want to evaluate 10,000 x values, that's fine, that's still doable. However, if you have 3 dimensions and 3 variables, and you want to do it for every possible x, y, z, and each of them have 10,000 possibilities, then you have to evaluate 10,000 times 10,000 times 10,000 points in a 3-dimensional space. And that's going to take you a ton of time. So what alternatives do we have aside from grid search? Well, an alternative is to turn optimization into the root finding problem of solving f prime of x is equal to 0. In other words, we're no longer finding the optimum of the function, but instead finding when its derivative is equal to 0. For this function, f prime of x is equal to this thing over here. And based on this, we can create a function called f prime, which takes value x and outputs this fraction. And then we can use other methods that we have learned to find its root. For example, we can use uniroot to find its root. So we can do uniroot of f prime, where the lower bound is 2 and the upper bound is 10. And this, I'm using onList here so it can be printed horizontally instead of vertically. Otherwise, it will overflow the screen. So we can see that in the output, it gives us a root around 5.79. The f function evaluated, actually the f prime function, which is the derivative function evaluated here, is close to 0. And it took 7 iterations. We can also try to find the root using the Newton-Raphson method we have learned. Strictly speaking, to find the root of f prime using Newton-Raphson, we need to find the derivative, which is f prime prime. So in other words, we need to find the second derivative of the f function. Here, instead of trying to find what is the analytic formula for the second derivative, we will numerically approximate the second derivative using numerical differentiation. That is, we're going to evaluate the slope of the tangent line, or the slope of a line going through f and f prime of x, and x plus h, and f prime of x plus h, where h is a really small number, for example, 10 to the negative 7th power. We will create a generic function for approximate univariate Newton-Raphson root finding. This function is going to take a smooth function f as its input, and it will return a root of the function. So here's the generic Newton-Raphson function. This function takes the function f, which is the function that we want to find the root for, the tolerance, an initial value, and the maximum number of iterations as its inputs. first step we'll do is to specify the h value, which is used for approximating f prime of x. So let's set it to be e to the negative 7th power. And like before, we will set the iteration number at the beginning to 0, and we will evaluate the f function first at the initial guess, x0. Subsequently, we will iteratively update the x value. So let's set this scalar x to be x0, and this is the thing that we're going to update in each Newton-Raphson iterations. While the iteration number is still below 1000 and the absolute value of fx is still greater than the tolerance, we will first approximate f prime by looking at the slope of the line going through point x and s plus h. And then we call this object fpx, which is a numerical approximation for f prime evaluated at x. And then we will be able to implement the Newton-Raphson update step, where we set the next x value to be the current x minus fx divided by f prime of x. We will also evaluate fx again at this updated x value, and we will increment the iteration count by 1. We're going to return a list that contains the solution, which is the last x value, the value of the function f evaluated at the solution, as well as the number of iterations it took for this procedure to terminate. So for this example, let's look for the root of f prime of x using the Newton-Raphson method, and let's set the starting value to be equal to 2. So we can use the function we have created, and we feed in f prime, which is the function we want to find, the 0.4, and the initial value x0 equal to 2. And here are the outputs of the function. It gives us a solution around 5.79. As you can see, it's really close to the solution given by uniroot. And the f prime function evaluated at this point is around 5.27, and it took 7 iterations. The f prime function evaluated here is really close to 0, and it took 7 iterations. So please note that here we are finding the root of the derivative. In other words, we are finding an optimum of the original f function. In this case, the maximum of the f function is attained somewhere around 5.79. Now let's turn into an R function that is designed for one-dimensional optimization. This function is called optimize, and it searches for local minima and maxima in a supplied interval. It utilizes a combination of something known as golden section search and successive parabolic interpolations. And note that here, because we're using the optimize function, we are no longer looking for a root, but instead we are root of f prime, but instead an optimum of the f function. So now the input should be the original f function instead of f prime. And also by default, this optimized function will search for the minimum. So we need to specify maximum equals true over here. So here's the code for calling the optimized function to find the optimum of the f function. We need to specify the function f, the lower and upper bounds of the interval where we want to look for the solution or the optimum, and we want to say maximum equals true. And we can see that the resulting maximum estimated here is also around 5.79. And when x is equal to 5.79, the objective function is maximized and the objective is around 1.055.